Welcome back. We are continuing on with our sojourn into exponential functions, and specifically, we're having a look now at logarithms. So, if you're following along, this will be the continuation and finishing of lesson three in the ILC. And we're looking at now logarithmic notation as well as some properties. And so, for today, we're going to be having a look at an introduction to logarithms, the logarithm notation, converting between exponential and logarithmic form, evaluating logarithms, as well as a section where we'll talk about some properties of logarithms. And so the big thing to know whether we're going to be successful for today or not is that we should be able to convert between the exponential and the logarithmic form of uh, an equation. And just keep in mind that in terms of like the key thing to pull out, it's being able to convert from a logarithm to an exponential or from an exponential to a logarithm is pretty much the key to solving most of these kind of questions you're going to run into. Additionally, we'll be able to use this to help solve some and evaluate logarithms. And so here, uh, just as a quick review of kind of what we're getting into, we're going to be sketching the graph of f of x equals 1 over x, one half to the power of x, as well as the inverse, which is what is going to be hinted at to be called the logarithm. Okay. And so remember that notation is f negative 1 of x. And also we're going to get that so-called line of reflection. And so let's go ahead and get to this. What's the best way to go about this? Well, usually what we want to do is just to make a quick table of values to kind of help assist us. For exponentials, usually 3 points is enough, but for learning purposes, we'll say use a few more points instead. So here we're going to be sketching the function y is equal to 1 half to the power of x. And then afterwards, we can sketch the inverse. Okay, so normal values to pick for x, let's pick -2, -1, 0, 1, and 2. And when we insert this into the function, remember this will be 1 half to the power of -2, 1 half to the power of -1, 1 half to the power of 0, 1 half to the power of 1, and 1 half to the power of 2. And so when we do this, 1 half to the power of -2, if you want to, you can type this in on your calculator. And again, I'm using the Desmos scientific calculator, and which will be fine for this course, but you can also use your own calculator. You can type these in or kind of evaluate what you know they should be. So -1 half to the power of 2 is going to be 4. -1 half to the power of 1 will be 2. -1, sorry, will be 2. 1 half to the power of 0 will be 1. 1 half to the power of 1 will be 1 half, but we'll write it just as 0.5, so that is easier to graph. And similarly, 1 over 2 to the power of 2 will be 1/4, but we'll call it 0.25, again, because it's easier to graph. And so when we go ahead and graph this function, let's go ahead and graph these key points. -2, 4 is the first point, -1, 2 is the next, 0, 1, 1, 1 half, and 2, 0.25. And you kind of just do your best you can to plot some of those decimal ones. And so now we're going to connect this with a smooth curve, and our arrow extends forever. And so now, if I want the inverse, f comma the inverse function, f -1 of x, all I need to do now is to swap the position of the x and y values in my table that I previously found. So instead of -2, 4, that becomes the 0.4, -2. -1, 2 becomes the 0.2, -1. 0, 1 becomes the 0.1, 0. 1, 0.5 becomes 0.5, 1. And 2, 0.25 becomes the 0.25, 2. And so when we go ahead and graph these points, 4 comma negative 2 is down here, 2 comma negative 1 is here, 1 comma 0 is here, 0 0.5 comma 1 is here, and 0 0.25 comma 2 is here. So we end up getting this shape. We'll miss that line. Let's try connecting these again. And again, just try to connect these as best you can using a digital pen, so it's a little bit easier for me to make mistakes. So now, only other thing we want to do is to go ahead and label what these are going to be. So this blue curve, or the dark blue curve, I should say, is the y equals 1/2 to the power of x, and this teal curve is going to be the inverse, whose equation is x is equal to 1/2 to the power of y. Now, this notation looks a little bit clumsy because we typically like to explain functions in terms of y is equal to something. So in this case, what we're going to be looking at is that this function will actually be y is equal to log base 1/2 of x. And this is actually what we're going to end up studying over the course of today. The line of reflection, of course, is the y equals x point. And there it is here. So there's a nice little review of the topics that you needed, as well as I believe this will help with key question 1 of lesson 1. Okay. So in general, when we talk about an introduction to logarithms, all functions have an inverse, but the inverse of an exponential function has a special name. And so we call the inverse of an exponential function something called a logarithm, and new notation is introduced to denote this function. So instead of using the clunky notation of where before we said that the inverse of the exponential was this clunky x is equal to a to the power of y, we instead have y is equal to log base a of x. And all that represents is that it's the inverse of the exponential function. Okay. So again, here was the graph of what we had from the lesson of last time, where this was the generic y is equal to a to the power of x, where a is greater than 1. Here, this function looks a little bit different because we had a base of the exponential be between 0 and 1. So it's going to cause a reflection instead. But here, this is what they happen to look like. Okay? And so our focus of today will be talking about this curve here that I highlighted. This will be the equation y is equal to log base a of x, which is identical to what we just wrote. A couple of ways to say this. I should mention y equals is the equivalent form. And so when we want to talk about what this means, this is said as y is the logarithm of x to base a, or y is equal to log base a of x. I actually, in terms of like, if you want to be, say, explain this to somebody the first time, we would typically use this first form. But from a teaching perspective, and then yourself from a learning perspective, we end up saying the second version a lot quickly, just because it's faster to say. So y is equal to log base a of x, or log is, or we might say that y is equal to log base a x. So we might say log base 3 of 7, or log base 3, 7, something like that. But in general, that's how we typically would say this, though. Okay. And so before we get into some examples of this, this is the section where I want to talk about properties. And so instead of talking about in generalities what this looks like, I chose a specific example for us in order to talk about these things. And so I'm going to use y is equal 2 to the power of x, which is going to be this red curve here. And so, for example, like this point up here happens to be the point 3 comma 8. So if you say 2 to the power of 3, that does equal 8. So we know that that's going to work. And we're going to be talking about the inverse function, which is going to be log y is equal to log base 2 of x. Okay, so let's talk about the domain. So the domain referred to what x values you are allowed to have. And so if you have a look at this red curve here, as far as x values is concerned, we would continue all the way out to negative infinity. So you can do 2 to the power of, say, negative 99, and you get some tiny number, completely fine. As well as you can do 2 to the power of some large number, and that'll also give you an answer. So here, the domain we would say is x is an element of all real numbers. Well, what about the green function, this y is equal to log base 2 of x? Well, for this one here, if you notice for x values, we seem to be getting very close to this 0 value, but then it doesn't kind of get there. And that's because you can't take the log of a negative number. So if I try to, and if you want to use the Desmos calculator, it's under function here, and you can click this log button. Say if I want to take the logarithm of 0, that's undefined. Additionally, if I try to take the log of, say, some negative number, that's also undefined. So we can't take the logarithm of 0 or negative numbers. Instead, we must take the log of only positive values. So we need our x value to be greater than 0. Any number is greater than 0 is okay, but x must be at least as great as 0. Sorry, it must be greater than 0. Okay. The range refers to the y values. And so if we have a look at this, on the red curve, we get really close to 0. And again, when we're looking for range, we want to think about this in terms of how far up the graph we can go and how far down the graph we can go. We can continue on forever in the positive direction, but we can't quite get to 0. And that's because if you take 2 to the power of some large negative number, you get close to 0, but not quite 0. And so the range will be y is an element of all real numbers, but y must be greater than 0. Similarly, for the range of log base 2 of x, if you notice here, this function increases very, very slowly, but it increases. So if we can continue this green line, it'll forever go upwards, just very, very slowly. And as we move down leftwards, we actually shoot down towards negative infinity fairly quickly. So the range in this case will be y is an element of all real numbers. It can be whatever you would like. And so if you notice, on the lesson of last time, we talked about how domain and range are related to each other insofar as that if you have the domain of y equals 2 to the power of x, so if we're looking at the domain of this, that'll be the same as the range of this. And the domain of x of log base 2 of x is the same as the domain of y equals 2 to the power of x. So they're related, but then we just swap the x and y's. Okay. For y equals 2 to the power of x, what's the x-intercept? There is no x-intercept, so it's not applicable. What's the x-intercept of y equals log base 2 of x? Well, it's going to be a 1 here. So we would just say that it has an x-intercept of 1. What about a y-intercept? Well, we can see that on the red function, y equals 2 to the power of x, it crosses the y-axis here at 1. So it has a y-intercept of 1. And by a similar token, it has the logarithm, y equals log base 2 of x, has no y-intercept. So we would say it's not applicable there. And just like before, we notice that the domain, in this case, that y equals 2 to the power of x had no x-intercept, which means that it'll then have no y-intercept for the y equals log base 2 of x. Okay, so again, kind of mirroring what happened from above. What about the vertical asymptote? Well, for y equals 2 to the power of x, there is no vertical asymptote. It just kind of gets infinitely close to 0. It doesn't quite get there. It gets very close to it. And so we would say that the equation of this will, we would say that there is no vertical asymptote. Oh, got my colors mixed up here. Let's try this again. Red. So this would be not applicable. But the log function does have one. So you can see it gets kind of close to 0. And so we would say that the equation of this would be x is equal to 0. For the y equals 2 to the power of x, we would say it has a horizontal asymptote of y equals 0. And similarly, it has no horizontal asymptote. So again, we can see that these are matching up again. Okay. So with that in mind, let's continue onwards. Okay, so here's the graph that we did at the start. So at the start, we did the example of where we had y is equal to 1/2 the power of x, and the logarithmic equivalent is y is equal to log base 1/2 of x. This is that example here. Okay, so all the properties that I talked about with respect to when the case was a was greater than 0 still applies here. Okay, in this example here, this happens to be a case where a equals 0.4, but as long this is true for any value between 0 and 1. Okay, so the properties is still the same, meaning that we can apply this the same way. Okay, so here's the key to how making all of these things work. So now the interesting thing becomes, well, how does this work? What do we do with it? Well, if we want to convert from the logarithmic to the exponential form, we know that the number is equal to the base to the power of the exponent is the same thing as the exponent equaling the log base number base of that number. And it's worth noting that when I talk about log base something, so if I have like log base 2 of x or log base 3 of x, this is the same kind of base I'm talking about as, say, 2 to the power of x or, say, 3 to the power of x. So you want to be thinking about, when I talk about base, you want to be thinking log base 2 as being the same thing as 2 to the power of something. And so how does this work? Well, as an example here for you, I have the logarithmic form and the exponential form. I have 4 is equal to log base 2 of 16, but also 16 is equal to 2 to the power of 4. Okay? And so you should be able to, this should become something you want to master, because you will need to do this quite often when we want to go ahead and solve some of these things. Okay? And so example 1, we're going to rewrite each equation in logarithmic form. Later, I'm actually going to show you how to type some of these things in on the last example, and we'll come back up here to verify some of these work. Okay? And so 5 to the power of 2 is equal to 25. So have a look at our formula. So here we have the number, I put in red, is equal to the base, which is blue, to the exponent. And so in logarithmic form, we would say the exponent, which is going to be 2, is equal to the log of the base, which is going to be 5 of 25. Okay. That's how they're going to be related to each other. Now keep in mind, I also could have written this the other way. I could have written this as log base 5 of 25 is equal to 2. And most often, that's usually how I end up writing it, as well as how most people end up writing these things, is they write the log first. And I use a cursive L here. You can just use regular font as well. So log base 5 of 25 equals 2. I just use a cursive L because I often find that that reduces the chances of making an error of some kind. Because then I'm like, oh, okay, that's not like a 10 with a G on it. Say for we're accounting for bad writing, which sometimes I have. Okay. What about 2 to the power of 6 equals 64? Well, this will become, and again, the exponent will be 6 equals log base 2 of 64. Okay. We're going to highlight where these things go. There's the 6. There's the 6. The base of 2. The base of 2. And equals to the number is the number. Okay. Sometimes people put brackets around the argument of the logarithm. That's just to show that the 64, it's log base 2 of the entire entity of 64. So if you're worried about clarity of some kind, you can just, it's also okay to write it like this. Usually I do not, but again, nothing wrong with that. And in fact, some of the examples later will have brackets around there, just so that we're clear about what this looks like, but you don't necessarily need the brackets. Okay. If you're watching this on YouTube, now would be an excellent time to go ahead and pause the video, try out examples C to F for yourselves, just to make sure you kind of understand how we go ahead and convert these. Okay. So give you a few minutes to pause the video. Okay, let's see how we did for these. And so we have 4 to the power of negative 2 is equal to 1 over 16. So again, using our example from above here, we can see that it's the exponent, negative 2, is equal to log base 4 of 1 over 16. And here it's actually appropriate to put brackets around the fraction, just again, because sometimes what ends up happening is if you try to write these things, say negative 2 equals log base 4 of 1 over 16. Sometimes your 1 over 16 can kind of start to drift downwards. And so it is actually proper etiquette to go ahead and put brackets around there. And again, if you so wish, you could write this as log base 4 of 1 over 16 is equal to negative 2. Okay. What about 8 to the power of 0 is equal to 1? Again, we're just going to have a look at our notation again. This will be 0 is equal to log base 8 of 1. Or if you prefer, log base 8 of 1 is equal to 0. Okay. Letter E, we have 216 equals 6 to the power of 3. And again, it's worth checking and confirming. Yes, 6 to the power of 3 is 216. And so here, what we have is 3 is equal to log base 6 of 216. And again, if you want, you can put brackets around it. Or we can say that log base 6 of 216 is equal to 3. Okay. Lastly, but not leastly, we have 1 over 81 equals 3 to the power of negative 4. And so just as a calculator check, that is the case. It's going to be 1 over 81. And so this is going to be the exponent. Negative 4 is equal to log base 3 of 1 over 81. And again, just to kind of highlight the difference here. There's the exponent. There's the exponent. Here's the equivalent in the logarithmic form. Here's the base. Here's the base. And 1 over 81 is the number, and that's the argument. Typically, what I found in my experience is that students will never usually mix up where the base goes. They usually mix up where the other two go. So that can happen on occasion. Okay, let us continue on. Okay. And so now we're going to write each of these equations that are in logarithmic form back into exponential form. And again, the key to solve when we're going to be working with these tomorrow is being able to freely go between the two versions is critical in order to make this work. So let's have a look here. So we have, and we'll use this example from here just kind of as a guide to help us. So if we have log base 7 of 343 is equal to 7, well, it should make sense then that 7 to the power of 3 is equal to 343. Okay, exactly like what we had from before. Okay, what about log base 2 of 16 is equal to 4? Well, we would say that 2 to the power of 4 equals 16. Okay, and again, we're just mimicking the exact same steps that we had from before. If you're ever unsure, go ahead and type these in just to make sure that it works for you. So here, 2 to the power of 4 is going to give us 16. Okay, or if you prefer, 7 to the power of 3 is at 343. If you ended up typing one of these things wrong, say, for example, you told me that 2 to the power of 16 was equal to 4. When you go to try to type this in, well, you know that can't be right because this answer should be 4, and 2 to the power of 16 is some large 65,000 number. So that's a nice way to check to see whether these things are, as you're working through them, are correct or not. Okay, what about example C? We have log base 3 of 141 over 243 is equal to 5. And so it'll be the base, which is 3, to the number equals the argument. So it's going to be 1 over 243. So the way I like thinking about these is I say, oh, it's going to be 3 to the power of that number equals this. So I look at the logarithm, the base of the logarithm, and then I raise it up to the number on the other side of the equal sign. That's the easiest way for my brain to kind of look at this and see what to do. Okay. And so for D, if we have log base 2 of 1 over 64 equals negative 6, then I take 2 to the power of negative 6. Okay. So 2 to the power of negative 6 equals 1 over 64. And again, we can take our calculator on the left here and type this in to make sure that all seems to be going according to plan, which it does in this case. Actually, the nice thing about why I like this Desmos calculator is if you notice I'm clicking this fraction button here, there's the decimal equivalent, which is useful if I want to graph this. But in terms of making sure we understand, we prefer to keep it as a fraction. So there it is here. Okay. Question letter E. What about 0 is equal to log base 5 of 1? Well, first thing I see right away, it's the base is 5 to the exponent. And so this will be 5 to the power of 0 is equal to 1, which we know is the case. That's the exponent 0 that we studied on the first lesson. And lastly, but not leastly, we have a little bit of an unusual situation here. We have log base B of b to the power of 2 equals 2. At this point, it's actually quite helpful to introduce brackets. So we were going to say instead log base b of the quantity b squared, or b to the power of 2 equals 2. And so, just like before, we take the base of b, put it to the power of 2. So this will be b to the power of 2 is equal to the argument, which was b to the power of 2. And you're kind of looking at this now, thinking this is a little bit suspicious, but this is a pretty important property. In general, or I should say specifically, in general, if you have log base b of b to the power of something, that's actually equal to that something. So if I have log base b of b to the n, that's just equal to n. So if I have log base b, let's not do base b, let's do base 7 of 7 to the power of 3, that'll be just equal to 3. Okay, we're actually going to be, this property will become useful for us, or more useful for us, in the lesson of next time when we go ahead and study some ways to solve these. That'll be lesson 4. And so there's all kinds of neat little properties that can start to be applied once we start working with these logarithms. Okay. So small note, we're going to consider the following. And this note is going to be on the common logarithm. Consider the following. Log base 10 of x is equal to log x. So when you see log x written without a base, and I should mention in this course, because in some future ones, they might make some stipulations, but for now, for our purposes, when you see log of x, we assume this always means base 10. This is what we call the common logarithm. And this is the important reason why. All scientific calculators have a logarithm base 10 button. Now, some calculators are actually quite helpful in that they have calculators that give them log base of whatever you need. Say if you want to evaluate log base 7 to 50, there's calculators that can do this. However, not every calculator can do that. However, all calculators do have a log base 10 button. So if you have a look at this Desmos one here, I only have a log button. Now, there are different buttons that have log base 8, like whatever you need, button instead. Okay, so what's the point of this now? We can actually we can solve this equation that we stated from the last lesson. So in the last video, I said, hey, if I want to solve 10 to the power of x equals 2500, I knew that 10 to the power of 3 was equal to 1,000, and 10 to the power of 4 was equal to 10,000. So the answer to this question is that x is probably between, well, it has to be between 3 and 4. And so we did a test value. If you recall, if you don't, that's okay. Or if it's your first time looking at the lesson, we said, oh, what about 3.5? Like, it's still a bit high, but it's in the right direction. So we can actually use logarithms to solve such a question. So typically when we were working with exponentials, we actually want to end up solving for the exponent quite a bit. And now logarithms let us do that. And so if I want to solve 10 to the power of x equals 2500, remember that the logarithmic equivalent of this will be log base 10 of 2500 is equal to x. And I mentioned that if you had a base 10, you can just write this instead as log of 2500 is equal to x. Or if you prefer, you can print out the log instead if you like, as such. Okay, so let's type this in now. So if I go over to so that you can see main, ABC, then we want to go to function here, click on the log button, go back to main, and then type in 2500. And so we have that the answer to this will be 3.3979400 something, something, something. Typically, you end up usually rounding to 3 or 4 decimal places. So let's say we're going to have round this to 3 decimal places. So that would be here. So we're going to make this 3.398. So what does this mean? Well, if I take 10 to the power of 3.398, I will get about 2,500. So let's test that out. 10, oh, 10 to the power of 3.398. And so here we actually get a more exact answer is 2,500.345. If you wanted to be a bit more accurate, you could take more decimal places. So say, for example, what if we took 10 to the power of 3.3979? And if you did that, your answer gets a bit closer, but you can see that since we're dealing with the exponent, the decimal places actually quite matter how many we round off to. So here, if we put a 9, we actually are short answer by 0.24. And if we tack on a 4, it gets a bit closer. And so in general, we tend not to round exponent answers to 1 decimal place. So say, for example, we call this 3.4. We actually end up being off by 11. So hence, customarily, usually 3 or 4 decimal places is appropriate when we're trying to calculate what these are going to be. Okay. And so for our purposes, I will only use the base 10 button. So let's have a look. Okay, let's evaluate some logarithms. So let's type in, we're going to evaluate the following with the use of a calculator. We're going to round our answers to 3 decimal places. Okay, sure. First one is log of 2,000. So we're going to type in log of 2,000. So this is going to be 3.301. And it should be mentioning that if you want to check this, if I take 10 to the power of 3.301, I get about 2,000. So I use this approximately sign and I get about 2,000. Okay. What about log of 0.004? Sure, we can do that. So let's go, oh, let's not type it in there. Let's type in log of 0. And so if you notice here, log of 0 is undefined because that's a vertical asymptote that we saw from above here, correct? So just wanted to make sure you saw that. Okay, so 0.0004. And so the answer to this question is negative 3.398, some small number. And so again, I should mention that if you take 10 to the power of negative 3.398, you'll get about 0.0004. And so for this last one here, we've got log of, that's a 1 followed by 9 zeros. So log of 1 billion. So you're probably thinking that's going to be a big number, right? It's a pretty reasonable guess. And if you do that, log of, and you can actually watch on the display as I type this in. It's got this many 9s. There's our answer here. The answer to this is just 9. And so you might be thinking like, whoa, that doesn't go up. You mean if you do log of a really huge number, it's a small answer? But actually, yeah. And if I type in some more zeros here, it goes up pretty slowly. And so for each time we add a zero, we only increase our answer by one. And that has to do with the fact that if you notice from before, when you had something like 2 to the power of 10, and then you did 2 to the power of 11, 2 to the power of 11 is much bigger than 2 to the power of 10. However, when we're doing the log side of it, when you try to type in these huge numbers, they actually don't go up by that much, because whereas the exponential increases by a ton, the inverse of that is that the logarithm increases by a tiny bit instead. So we can type these into the calculator, not a big deal. And so I mentioned that I was only going to use the log base 10 button. And this is what I'm talking about here. So a logarithm can be expressed in terms of base 10 using something called the change of base formula. So if you have log base b of m is equal to log of capital M over log of b, where b and m are greater than 0, b is not equal to 1, and so forth. This formula is called the change of base formula, and we will use this at least for today because most calculators have a log button of some kind, and you want to find your log button on the calculator as well. Okay, so what's the point of it? Well, we know that if you have log base capital B of capital M, that's equal to log of M over log of B, that the base of the logarithm becomes log of just B on the bottom, and the argument M becomes log of just regular M on top. And it should be noted that when we talk about these things, these are log base 10 of capital M and log base 10 of capital B. We just don't write the capital B there instead. So what does this become? Well, we have log base 15 of 20 is equal to log of 20 divided by log of 15. Oh, I deleted a whole bunch of it. Oops, there we go. So I'm just trying to highlight for those who are going to be watching this later on YouTube. Okay, so the change of base formula, super helpful. So we can actually type this in and see what this looks like. So on our calculator here, you want to hit this fraction bar first, and you can also I do encourage you now, if you don't have a fraction button like this, do practice typing these things in, just so that way you're used to what they look like, so you understand how to do this with your calculator. So this is going to be log of 20 divided by log of 15. And so this is going to be equal to 1.106. And so what this means is, if I take 15 to the power of 1.106, I get about 20. And so if I do that, 15 to the power of 1.106, it equals about 20. Because again, we rounded off the decimal places a little bit early. Okay. And you can see, check one of these ones that we did from before, right? So say, for example, we wanted to have a look at I just accidentally deleted a bunch of this, but that's okay. There you go. If you wanted to have a look at log base 2 of 64, log base 2 of 64, to type that in, we should be typing in log of 64 over top of log of 2, and the answer to this should just be 6. And so we type this in, log over top of the log. And so this is going to be log of 64 over log of 2. And we can see we do get 6. So super neat little handy formula for helping us to evaluate these things. And so we're going to apply the change of base formula to solve. And when I say solve, what I really mean is I should be using the word evaluate here. So I will. the following. So log base 1.04 of 2. And so we know this is the same thing as log of 2, the argument, divided by log of 1.04. And so when we type this in, oh, hold on. I have a fraction button here, so I'm going to make use of that. So it'll be log of 2 divided by log of 1.04. So this is equal to 17.67, I guess, 3. Question doesn't specify, so I'll just choose 3 decimal places for our answer. Okay. And again, what does this mean? Well, if you have a look at this answer, the question, that means if we take 1.04 to the power of 17.673, we should get about 2. And again, we had to round part of our answer off, right? So our answer will be off by a tiny bit. So if we take 1.04 to the power of 17.673, we get about 2. Actually, this one's pretty good. It's fairly accurate. Okay. And so I'm going to stop kind of showing just to show that these answers work, and we'll just kind of go through these. So log base 8 of 17 is the same thing as log of 17 divided by log of 8. And so when you type this in, log of 17 divided by log of 8. Now, if you're watching on YouTube video, you're kind of watching me like kind of finagle and get used to trying to type these in. If you're watching this on, or listening to this on the radio Zoom, you're seeing me just try to type these as possible. Not going well, but here we are. Okay, so log 17 divided by log 8 is going to give us 1.362. And again, we'll take 3 decimal places for rounding purposes, and that's going to be good enough. Lastly, but not leastly, we have log base 3 of 10 is equal to 1. Now, in terms of this is where it becomes useful to think of converting these over to the exponential equivalent. So if I saw normally log base 3 of 10 is equal to, say, something, then the question becomes 3 to the power of something should equal 10. So before typing this into the calculator, I'm like, okay, well, 3 to the power of something equals 10. It's going to be 2 point something, because I know that 3 to the power of 2 is 9, and 3 to the power of 3 is 27. So it's 2 point something for sure. So that's a way I can help try to remember if I'm doing this correctly or not. And so consequently, log base 3 of 10 is the same thing as log of 10 divided by log of 3. And so when I go ahead and type this in, it'll be log of 10 divided by log of 3. And it's actually 2.096 in this case. And again, we'll take 3 decimal points. And so that's how we're able to easily convert using the change of base formula. Like I said, in order to complete, in this lesson, I believe is what we called lesson 3. Key question 1 was being able to create a table of values and graph what this equation looks like. And then for the rest of the lesson, it was either converting these from either exponential to logarithmic form, from logarithmic form to exponential form, or being able to just kind of write what these things mean. And again, I gave you the change of base formula as a way for you to test to make sure that these answers are going well. And also then, so that way you can see kind of how these things all fit together. And with that, I think that's a good place to stop for today. So with that, I wish all of you the best of luck and have yourselves an excellent day.